I'm Holt Hanley here with Neil Lareau, who I would put in the category of top fire weather experts in the country and also best fire weather accounts to follow on Twitter. But if you want to just formally introduce yourself, I'll throw it over to you.
Sure. Thanks, Holt. Yeah, so I'm Neil Lareau. I'm an assistant professor at the University of Nevada, Reno, and formerly worked at the Fire Weather Research Lab where Holt has been working. But yeah, my research expertise and focus on wildfire plume dynamics and the way we go about trying to understand kind of the way the atmosphere responds to wildfires using weather radars and lidars to look at the development of these big convective columns and sometimes fire-generated thunderstorms that we call pyro-CVs, and in even more extreme cases, fire-generated tornadoes that can develop with these events and all the associated phenomena that go with it at the surface, like long-range spotting of embers. And yeah, so that keeps me pretty busy at this time of year.
Yeah, so I think you just mentioned a couple of the main reasons I wanted to talk with you today. One, I was thinking back to, it was the first fire that I ever got to go to, is that one in Utah. And I remember just got to sit with you and watch that fire for like 6 hours or something. And then just I was just amazed looking at the smoke plume, the big flames, and that was like enough for me. But hearing you explain what was actually going on it just made the entire thing way more interesting. And then with the McKinney fire that just happened, where we had that big Pyrocumulus Cloud, I thought you would just be the perfect person to kind of dive in and ask some questions about that.
Yeah, and I mean, I agree with you that fire in the Fish Lake National Forest, which was a stand replacement prescribed fire lit with heli torch in November, produced this amazing upright convective column that developed periods of rotation, deep pyrocumulus clouds. And it was one of the more exciting ones that I've been to too, and that we were such a great vantage point to be able to just watch the whole evolution of that. And so yeah, that was a really formative one. And one of the papers that I'm working on now is an analysis of that plume development. But like we were chatting about a few moments ago, that just every season there's these new amazing plume examples, and so it's hard sometimes to wrap up these older analyses, but hopefully have some time to get to those. But yeah, the McKinney fire obviously produced some really deep fire-generated thunderstorms, as well as interaction with ambient thunderstorms and all sorts of interesting / terrifying phenomena for the firefighters. And really the big day, I guess, let's see, that was the afternoon of the 29th, I think, into the 30th. It produced these towering plumes up to about 40,000+ feet in altitude that were triggering their own fire-generated thunderstorms, their own lightning strikes. And really, for me, looking at that event, probably the scariest part of it was the interaction with these outflows from other thunderstorms in the environment, which people often describe winds on fires as being erratic, and that's always true to some extent. But I think this is kind of the paragon of that, where we have winds switching directions by 180 degrees back and forth across the fire, and providing really active pulses on one flank of the fire, then the other flank of the fire. And obviously that's a really scary situation for firefighters, and makes it really difficult to understand what's about to happen next on the fire. And sort of just kind of going with this here, but the big difference right now with the weather pattern that we've been seeing is this persistent monsoon moisture that's been streaming northward into California. And that's really been setting up for these daily thunderstorms that we've been seeing, as well as the generation of the fire-generated thunderstorms due to the availability of moisture, especially up in the mid or upper levels of the atmosphere. It's really kind of different than sometimes that hot, dry, and windy fire weather that we associate, especially in these hot summer afternoons. It's much more the thunderstorm variety, which is particularly scary.
Yeah, I made one quick like thunderstorm explainer video yesterday with how it interacts with wildfires, and I was saying that there's almost like two sides of the coin. Like it could be either good or bad for wildfires. Like it could be good for fires, like what we've seen the last. It seems like we've seen the last couple days on the McKinney where it drops some rain, and then that rain brings some moisture into the fuels and slows the growth down. But then all the things that you were just saying are the flip side of that coin, where it can lead to the gusty, erratic winds. It can lead to lightning, which is new fires, and then all of those kind of things that can lead to a rapid spread.
Yeah, and admittedly, from a forecast perspective, I think sometimes it's hard to know which flavor you're going to have on a given day, and some of it really is up to chance about whether or not you get a heavier precipitating thunderstorm directly over the fire or adjacent to the fire. If it's adjacent to the fire, you can get these outflow winds that impact the fire. If it's over the fire, there's still problems, but can lead to suppressed fire activity, like we've seen now for the past couple of days on the McKinney fire. And part of that too, the cloud cover, we've had a lot of what you might call convective debris clouds, where there was a really active afternoon, maybe over Southern California or over the Southern Sierra, even all the way down toward Las Vegas the day before, which puts all this cloud cover up into the mid and upper levels. And then the winds bring that up over the fire. And that can then, kind of shade the fire and lead to less active fire development on a given day. But so it's kind of hard to know, are you going to get that shaded kind of fire behavior, ambient clouds, or are you going to get deep convective clouds? We don't always have the ability to forecast that so well, which adds to the uncertainty, I think, on these fires.
Yeah, thinking about that forecast aspect, would you say it's more likely to have good thunderstorms if it's like a lot of moisture coming in, like say from a hurricane off the coast, and it's bringing in a lot of water vapor? And then the worst ones will be when the fire is actually just generating its own thunderstorm through all that like vertical motion?
Yeah, it's tough to say. I guess it's always a question of how do you evaluate what's worst? I think about like a fire like the Yarnell Hill fire, which obviously had profound tragic consequences, and that had to do with very active fire and then an adjacent thunderstorm with this outflow boundary that came across the fire and drove the fire in a completely different direction and overtook firefighters. The flip side is when it's generating its own fire-generated thunderstorms, it often has really intense fire behavior beneath that. The fire might be kind of driving that, so you're already in a state where the fire is extremely active. And then if that storm starts precipitating, it will, potentially create its own downdrafts and blow the fire out in multiple different directions. So I think they could be equally hazardous for a given fire, kind of depending on what's going on the fire ground that day. And so they're both really, watch out situations for firefighters, but they are different. The storm directly over the fire versus the outflow boundary that might be coming in from somewhere near the fire.
That makes a lot of sense. It's like if a thunderstorm is maybe like slowly moving in or even kind of grazing the fire, you get those outflow winds that would push the flames. But then when it's directly above the fire, that's where, like I was reading it about it, it almost sounds like a chimney or something, where the fire generates a bunch of heat, leads to rising motion. And then because that rising motion, it brings winds in.
Exactly. Yeah. And those inflow winds can then be the dominant driver in what the fire is doing and interact with the fire, and can especially lead to kind of like mass fire, where you have a lot of simultaneously combusting area, very strong inflow winds, really strong updrafts, and exactly then it's kind of a vicious cycle, right? As the updrafts get stronger, necessitates more air coming in, which kind of fans the flames, if you will, which further generates the updrafts, and you get in this feedback loop that leads to these plume dominated kind of fire behavior days. Yeah, and just the other thing I would say too, with the outflows that have been impacting it, you know, you never know which direction they're going to be coming from. It's one of those things, like sometimes we can see it in real time on the radar. Here's a thunderstorm right here, and you can actually see that outflow boundary coming in. But other times it's really catching you by surprise, and there might be other inflows coming in, or outflows rather, coming from other storms. I'm just thinking back to the afternoon of the 29th, you know, looking at the radar observations of the wind field, it was extremely difficult to decipher what was going on. There was just so many different airflow patterns simultaneously occurring. That would be very hard to make a decision in that environment.
Yeah, I remember seeing one of your tweets. It almost looked like the radar was like shifting back side to side. And then
Yeah,
you mentioned something about, I think you said evaporative downdrafts. Like, what exactly was going on right there? Because I looked at it and I had no idea.
yeah. So the shifting back and forth thing was definitely occurring. You know, you had the updraft column on one flank of the fire, and then just 5 minutes later on the other flank of the fire. And the evaporative cooling and the outflows that result from that are really what was driving that. We had precipitation forming aloft in the clouds over the fire and raining down toward the surface, but a lot of that wasn't reaching the surface. It's evaporating as it comes down. And evaporation is a cooling process. So every time those raindrops evaporate into the air, they're cooling the air off. And that air then sinks because it's colder than its surroundings. It comes down to the surface. And then when it hits the surface, it spreads out laterally. And that kind of, you could see that in the radar signatures, where just suddenly the air would kind of be flowing outward from a point near the surface beneath these downdrafts. And it was those downdrafts and their kind of spreading out that was making the fire jump around like that. And I think the webcam footage really showed that too, where you could just see, you know, almost a, you know, like weakly rotating column on one side of the fire, and then boom, it's over here and kind of dancing back and forth. Really scary stuff.
Yeah, that was a perfect description of how that works. So it's like the raindrops are coming down, they evaporate, that cools the atmosphere. And then that, because cool air likes to sink, that leads to more sinking motion, and then that can spread out the fire at the surface.
Yeah,
And then kind of what that made me think about is, does the opposite happen on the side of the thunderstorm where it's going up, where you get that air rising, as it rises, it cools, which would form those water droplets, and then that would release energy, right? Making it warmer and then lead to more updrafts.
yeah, exactly. And so it's a kind of a cycle, right? Of you have air coming down, it's kind of blowing the fire out here, just like you said. You're going to get a stronger updraft there as it pushes the fire into a new pocket of fuels. You get that strong updraft, and then it's going to generate cloud and precipitation, at least on these days with monsoon moisture around. And so, yeah, it was kind of doing that for hours through the night, Friday night into Saturday morning there. And I think around, must have been around like 1:30 or so in the morning, we then saw the fire. You saw kind of the ambient clouds, everything else going on around it dissipate. And then the fire became the main driver of thunderstorms at that point, and it generated the deepest storm of the day. You know, up to maybe 45,000 feet or so, and some new lightning strikes. And yeah, that's the part we've only kind of touched on, is that you know, the fire generated storms are literally generating their own lightning strikes here, which can cause new ignitions. And you know, and then we also have all the other potential ignitions from these kind of holdover lightning strikes. And we're going to continue to see that in the days to come. Yesterday afternoon, we had a lot more thunderstorm activity again across the North State. You know, if we get some drier periods, you know, we do still have the monsoon flow going, it looks like, through at least Friday. But there might be some drier periods in there, and we might see some new ignitions which will stretch resources and such if they really get going. But hopefully we can catch them early.
Yeah, certainly following this fire as it keeps going. I think that you mentioned one thing that was the biggest question mark I had about the McKinney fire, and especially like I woke up that morning and all of a sudden the fire was like 20,000 acres. And I remember the producer was asking me, and some resources were still saying 300, and then some were saying 20,000. I'm like, is there like a glitch going on? Because I'd never seen that before, where something went from 300 to 20,000 overnight. And I think the weirdest part of that was that it was overnight, because typically like thunderstorms happen in the afternoon. So was this just a situation where the fire got into one of those positive feedback mechanisms, or was there something else going on that caused it to have so much nighttime activity?
Yeah, those are all good questions. Yeah, I think your colleague Kate Forrest at the Fire Lab called this fire an insomniac, and I think that's a good description of it. Very active nocturnal fire growth, especially the first 2 days of the fire. I haven't dug into the details too much, but one of the things that we do see in the Coast Range is if you're above the nocturnal inversions and not directly in any sort of marine influence, and this fire is far enough inland that it's not really in that marine influence. There's a lot of elevated terrain there. It can be above those nocturnal inversions, in thermal belts, and also in extremely dry slots of air that reside above those inversion layers with critically low relative humidities sometimes. And that can really favor nocturnal fire activity. It's one of those things, it's like I feel like so many textbooks and so often we think about fire as having this strong daytime cycle, late afternoon, and that certainly happens. But in the Coast Ranges, we see lots and lots of events with intense nocturnal fire behavior, and I think this really fits in there with that. And it's just something that firefighters really need to be aware of in the Coast Ranges in particular.
Yeah, my original thesis project was going to be about downslope winds, and those typically happen in the overnight hours, right?
Yeah, you get the downslope, down valley sort of flows as the air near the surface is cooling, kind of negatively buoyant, runs downhill and pools in the valleys. And we can see that clearly. Like this morning, if you look at the satellite image, all the river valleys up around the Klamath National Forest are filled with dense smoke, and that's smoke that's been captured in those draining cold winds and pooling in the valleys. But there's a lot of terrain that sits up above that in there too. Although fortunately the fire seems fairly suppressed so far this morning.
Yeah, it seems like it's been luckily calming down over the last couple days. But you also just mentioned like a lot of the different kind of sides of the fire behavior triangle there. And I think a lot of people watching this might not have like the full wildfire background. So do you think you could just dive into like the 3 sides of the fire behavior triangle, like the fuel, winds, topography, and just a quick like explainer for any, like a little introduction to the people who don't have knowledge about that?
Yeah, so fuel, winds, and topography obviously are all gonna impact fire behavior in different ways. I always like to kind of start with the fuels because they're a necessary condition, right? Like you need combustible dry fuels, and in the absence of that, right, like nothing really happens, which is why we have such a seasonal cycle to fire. Obviously we have plenty of wind in the winter, but the fuels aren't in the right condition to be combustible. And then terrain is a huge driver of fire behavior, especially during kind of typical conditions. We expect upslope runs where the fire is basically, it's easier to combust the fuel on the upslope side of let's say you have one tree burning, then the uphill tree is literally closer and more directly exposed to the flames and the heat from the combusting tree, and so that tends to draw fire up slopes. And even when we see fire coming down a hillside, oftentimes what's happening is that the fire will kind of, maybe you'll have some logs rolling out or embers coming down the slope and creating new fire. And even though the fire is progressing downhill, it's almost making uphill runs and then coming down and up and down and up, and maybe making a run up through the crown of the trees. So it's kind of almost a ratcheting action, the way it will come down hillsides. So yeah, terrain is a huge factor. And up here in the kind of Klamath National Forest area, if you just kind of look at a satellite image of it, it's some of the most rugged terrain that you can find. The complexity of the topography is just, ridges, valleys, everything is steep. And so it's really hard to get ahead of fires in that sort of topography. And then winds are, one of the most variable components that affect fires. So, the fuels at a given time of year might be in a relatively consistent condition from one day to the next. The terrain obviously is not changing on the timescale of fires, but the wind is extremely variable and becomes one of the most critical drivers of fire behavior, pushing the fire into new fuels. And really, the most explosive fire behavior then happens when you get all three of these components coming into alignment, right? When you have fuels, terrain, and winds all in a condition that supports explosive fire growth. And so that would be dry fuels, winds aligned with an upslope topographic run, and for example, a southwest wind going up a river valley and driving the fire in the upslope direction or the up valley direction with critically dry fuels is often what we see for some of the bigger fire runs in the Sierra Nevada and in the Coast Ranges. And then the last one that you mentioned in there, these downslope winds, once we get into the fall season, wind becomes an even bigger component of this equation. And we see our offshore wind events, which kind of counterintuitively often drive fires downslope. So are almost reversing the terrain component sometimes, but the winds are so strong during those events that it can continue to drive the fire downslope as opposed to upslope and those sort of conditions. And those are the really dangerous fires that often come into towns as opposed to running up toward the ridge crests.
Nice. That was a perfect little masterclass on fire behavior triangle right there. Yeah, I always like starting with the fuel one too, because I feel like that's just like the most intuitive one. It's like anybody who's made a campfire, first off, you need the log in the first place. Then you usually want to start off with like the finer fuels. And then the log will also burn much easier if it's like dry versus a wet one. So that one, like anyone who's ever started a campfire, that one makes a lot of sense. Topography, I always think of that one, like if you're holding a match like this, it will like slowly burn down the match. But then if you tilt it up like that, it'll burn a lot faster. And then
great example. Yeah.
With the weather one, there's always like one question I have about the weather aspect. And it was something that I was trying to figure out when I did my own like master's thesis, where I was ranking all the different variables that can affect wildfire. And I was expecting relative humidity to be more important than temperature, just because like the drier it is, the drier fuels are, and then the faster fire is going to spread. But when I like ran my machine learning model, temperature ended up being like the second most important variable behind fuel moisture. And then it was above relative humidity, which made no sense to me. So I think my question there would be like, how is the temperature actually, like it makes sense that hotter it is, worse wildfire is going to be. But is it just because it's getting everything closer to its ignition temperature, or like what's going on there?
It's a good question. It's actually a little bit outside of my expertise in some ways. I think really talking to combustion experts about that is relevant. But I think one thing that I often think about is that these variables aren't necessarily independent from one another, right? So like temperature and relative humidity are effectively anti-correlated, meaning when the temperature goes up during most conditions in California, the relative humidity goes down. So when you're evaluating the importance of one of these factors, it might look like, for example, a machine learning algorithm might highlight, okay, temperature, but embedded in that temperature information is also kind of coming along for the ride, the relative humidity information. And in particular, we can get low relative humidity when it's not hot out. And so my guess is that what you're really seeing is that the algorithm is keying on hot and dry afternoons, as opposed to you could have cold and dry conditions. And so, you know, it's kind of both. Yeah, the fuels being closer to their ignition temperature means there is more, they more readily combust. The fire moves more quickly. You get probably more energy out of the fire as a whole. But yeah, almost always when we see the temperature go up, the relative humidity goes down. So you can't, I feel like you can't often separate them. And even to some extent, the wind speed too will be somewhat correlated with the temperature. The hot, dry afternoons get gusty winds because you get more mixing and it's bringing higher momentum air from aloft closer to the surface. And so, yeah, from kind of a scientific standpoint, sometimes we got to be a little bit careful because these variables are not independent from one another. They all move together. And so sometimes it's hard to pull apart the different influences. Which one is more important? Well, they're all behaving similarly sometimes.
Yeah, I think you just touched on like one of the biggest lessons that I learned this entire last year was when I was starting my research project. The first thing that I tried, I think I had data on 16,000 wildfire incidents, and then for each of those, I had every variable you could think of. And then the first thing I thought was just doing like nice little correlation plots, temperature here, acres burned here. And what amazed me was the lines were almost like flat. Like there was almost no correlation with any of these variables whatsoever. But then like there is some correlation, but it wasn't as strong as I thought it would be. But then when you put it into, like, the reason I ended up going with machine learning was it was able to kind of figure out how all the variables are interconnected and like the relationships they have with each other. And then it was able to play off on that, which I thought was very interesting.
Yeah, exactly. And it does kind of highlight the utility of these approaches of looking at multiple kind of contributing factors at once. And there's some other tools like multiple linear regression that can sometimes isolate the relative importance of one variable over another. And of course, yeah, I don't know, it's kind of amazing. But like you said, you know, I feel like for decades people have been trying to figure out what's the magic formula, you know, what's the perfect index that we can use for predicting explosive fire growth, or, you know, what are going to be the critical days on a fire. And there's lots of good approaches out there. But I also think it's such an incredibly dynamic and what I'd call nonlinear system. There's so many feedbacks in the system. When the fire gets hotter, the winds get stronger, strikes hotter fire. You get in these feedback loops that make it so that a given kind of index or something just from environmental variables may not be able to predict what's going to happen. And for me, the analog for this is just thunderstorm prediction. No one index is going to capture all of the, you know, severe weather threats that can be associated with thunderstorms, tornadoes, hail, downdrafts, outflows, lightning. And I think we need to really allow for fire to be this extremely complicated phenomena, and not think that there's just going to be the one index that gives you the answer, whether it's the Haynes index or the hot, dry, and windy index or whatever. They're all useful in various ways, but none of them are ever going to capture the complexity of the system that we're trying to understand. And I actually think humans can be sometimes quite valuable in the loop there, of you know, kind of integrating this information and kind of thinking critically about fire conditions and fuels and thinking about the whole fire triangle and integrating all this information. Always impressed by firefighters' ability to do that in real time.
Oh yeah. So you just reminded me of something that is a question I usually ask, because like throughout my like research, a lot of the papers that I've read, and then a lot of the stories that you hear about wildfire, like clearly climate change is playing a big role. Like the warmer it gets, the drier it gets, and then drier the fuels are, just more wildfire you're going to have. Also, like drought stressed trees, you then end up with a lot of dead material up there. But I do notice sometimes it seems like some sources will say it's like climate change is the only thing like driving wildfire. And it seems like they're taking a very complex issue and then tying it in with like one variable. Would you say it's like the biggest factor that's driving like the increase in wildfire activity we've seen recently? Or is it one of those things where it's like so complex it's hard to really measure?
Yeah, it's a good question. And again, kind of like outside directly of, things I don't necessarily like write papers about it, so I don't want to speak too strongly about it. But the again, allowing the complexity, I think, is important. Understanding what the baseline is. We have a fire climate, right? Like fire is part of that climate. We have changes in the state of fuels that are both driven by perhaps some natural variability, but also strongly influenced by management practices. And then we have the climate signal on top of these things. And I think about the climate signal as kind of like a multiplier effect, where you're taking a base state of something and kind of putting it on steroids. I think that there's been a lot of good climate analogies about it being like steroids. If you take a already good baseball player and juice them up, and suddenly maybe they're only hitting 10% more home runs, but that makes a huge difference in the outcomes. And I think climate is playing that role. I think you can kind of zoom out and think about it, and we see global signatures in a lot of these phenomena, in terms of increases in fire severity and things like that. And that kind of keys you into the idea that it's not a specific location or regional phenomena that is a driver for something. And then, yeah, I mean, at the end of the day, it's affecting the base state of the fuels. So going back to the fire triangle, the fuels are kind of the integrator of the climate. They are a slow response system in some ways. So they're integrating the cumulative effects of changes in climate. I think that's really where a lot of the signal is coming from. And so it is the fuels, but it's the fuels being a conduit for I think the climate signal. And so again, it's not to say that climate alone is the driver. It's a complex system, the interaction of these components, but it's definitely a major contributor, I think, to the signal that we're seeing. And heat is the primary driver for making a thirstier atmosphere, through some very basic physics of just a hotter atmosphere has a higher holding capacity for water. Water has to come from somewhere to go into the atmosphere, and it's basically coming out of the landscape. And as a result, the fuels are integrating that effect and are in a more combustible state more often, and maybe earlier in the year. And I think we're seeing the impacts of that in real time.
I think that was just perfectly said right there. That's a great little analogy about the baseball player on steroids, where it's like taking a baseline and then multiplying it up. But I also like what you said at the end there about like the atmosphere is thirstier. So it's almost like our atmosphere is like a small sponge in the past, and then now it's like a big sponge that can absorb a lot more water. And that water's got to come from somewhere. So it comes from the fuels, makes them drier, makes wildfire more extreme.
And it's the flip side of the coin that also makes hurricanes precipitate more, or flash floods episodically be more intense because it's basically amplifying the hydrologic cycle. As the carrying capacity of the atmosphere for water goes up, we have the potential to rain more out of it when it does rain. And so it's this kind of enhancing the hydrologic cycle on both ends. It's really the same two sides of the same coin, floods and droughts, and well predicted, I would say, by climate models. That's and not just climate models, not just these really intricate, complicated models, but just baseline physical principles, I think, give us a lot of this information about what we should expect. Of course, the big question is what to do about it. And I think that's where the conversation gets even more complicated when it comes to wildfire, because it's hard to imagine that there's no off switch for the climate warming that we're experiencing right now. And even if there were, we still live in a combustible landscape. And so mitigation solutions about resiliency to fire, whether it's through prescribed fire, mechanical reduction, the way we build and, human landscapes, towns, ultimately, I think that the near-term solutions for a lot of the kind of catastrophic wildfire stuff need to come from that, because I don't think there is a reasonable off switch that we can throw for the climate component. So we need to think about that, and we need to address that for many, many, many reasons. But there's a whole other end of what we need to be doing with fire, probably, to make immediate changes to reduce the risk to humans in particular.
Yeah, I remember right when I learned like the life cycle of CO2 in the atmosphere, that was when I realized that a lot of our solutions are going to have to be on like two different time scales. Like there's the ones we have to do right now, and then there's the ones that we'll have to do like over time. So definitely a complicated issue right there. But
Yeah.
You did remind me of one question I asked. You mentioned the hydrologic cycle.
Well,
And
yeah.
then it reminded me of a question that I meant to ask earlier, and we're running a little low on time, so I'll just make this maybe one or two more quick ones. But ties back into the thunderstorms, and like when you get those big pyrocumulonimbus clouds, obviously there's like a lot of water vapor in there. So I'll actually combine my questions into one.
Yeah.
First, like how do you identify when it actually is a pyrocumulonimbus cloud? Because I always thought it was just like you look at it when it looks like it has that kind of white puffy cauliflower shape to it. That was when you called out. But then somebody on my YouTube channel said that I called something a pyrocumulus that wasn't. So I thought I'd ask the expert here. And then the second part of the question is that water vapor in that cloud coming from the fuels that are burning up? Or is it from just like the atmosphere around as it rises? Or is it like a combination of both?
Yeah, all really good questions. So yeah, so the basic thing is that the plume is rising to a point that it cools enough to take any water vapor that's in there and force it from a vapor state where it's invisible into a liquid droplet state where it forms bright white clouds. So as soon as we see the bright white cloud forming at the top edge of one of these columns coming off of the fire, we're going to call that a pyrocumulus cloud. The transition to pyrocumulonimbus is associated with the next phase change, which is where the plume continues to rise deep enough that the water droplets are actually forced to freeze. And then we get ice crystal formation, which actually releases some more heat into the plume and helps drive the upper plume deeper into the atmosphere. And the transition to ice in the top part of the plume is also critical for developing things like charge separation that can lead to lightning. It's also critical often to the formation of precipitation-sized particles, things like graupel, and having a mixture of what we call supercooled liquid water in the updraft and ice and all of these kind of thunderstorm type dynamics that go on. But really, yeah, that distinction pyrocumulus over to pyrocumulonimbus has to do with freezing in the upper part of the plume. And that typically happens around -20 degrees Celsius onwards to -38 degrees Celsius. So very, very cold temperatures. So plume has to get quite deep, typically, you know, kind of on the order of 20,000 feet plus, to get that. Where's the moisture coming from? So this is a great and kind of classic scientific question. There's still some open dialogue about it, but the real story is most of the moisture is coming from the environment, not from the fuels. There is a contribution from fuels. They are releasing moisture when they combust, both through or mostly through your evaporating fuel moisture, but as it goes into the combustion process. But you know, probably something like 95% of the moisture in that plume is just coming from the ambient environment. And so in other words, the fire is ingesting the air that's in the environment, and it's getting heated by the flames, by the heat from the fire, and rising, but most of the water is coming from the environment. And a good example for how we know that are these sort of monsoon days versus non-monsoon days. We typically see the pyrocumulus and pyrocumulonimbus forming when we see a big influx of atmospheric moisture, not a change in the intensity of the fire. So it's really has to do with the environment that it's forming in. And so I think, I'm not sure if I hit all of the questions that you had there, but that's the long and short of it.
Oh yeah, that was a perfect answer right there. And do I actually have time for one more question you just want to do?
Yeah, let's go for it.
All right, perfect. Because I think this will be the one that people are probably the most interested in, because it's kind of the big name event that happens with wildfires. And it was actually one of the first questions that I asked you on that fire that we got to sit on, where like obviously the thunderstorms with wildfires are bad because that can start like creating its own weather. We talked about how the winds can lead to fire spread, all those different dynamics. But like the most extreme example is where that plume actually starts like rotating. And then in the most extreme example, like the car fire in 2018, is where you get a full-on fire Nato. So final question, what is causing that rotation on the plume that can sometimes turn into a full-on fire Nato?
Yeah, it's a big question with a long answer. A lot of different things can cause it, and I think we're still trying to understand all the different complexities that go into it. There are a couple of different flavors, I would say. We know now from looking at some fires like the Loyalton fire and the Creek fire, the Bear fire, all these fires in 2020, a very active fire season. One of the fundamental things that's happening in wildfires is that the airflow is coming in, and when we get a strong updraft coming off of the fire, it forces the airflow to split around the updraft, similar to the way a rock sticking out of a river forces the water to split around it. And then on the back side of that, we'll get two eddies, basically, and they're rotating in different directions. So air is coming in, splitting around the updraft, and then folding back in. So if you're in a river, you would tuck your kayak into that eddy if you wanted a break from paddling, and you could probably just sit there because the air is actually, or the water in that case, is actually going back the other way. It's not a perfect analogy for a fire because the fire is also drawing air in a way that a rock isn't doing. And so these flows are actually enhanced in wildfires. What seems to happen is that when we have certain wind shear in the environment or certain advancement of the fire front, one or the other of these eddies can get kind of favored in the environment and get fire within it. And when that happens, it also stretches the column out vertically. And so we have a source of rotation near the surface, and then something akin to what a figure skater does. So we have some weak rotation there in the environment, similar to maybe a figure skater. They start a spin with their arms out. And when they pull their arms in, to conserve the amount of rotation, the radius gets smaller, but the rotation gets stronger. In the case of a fire, the analogy is actually as the plume goes vertical and gets deeper, that's the same thing as a figure skater pulling their arms in. It stretches the column out vertically, collapses that rotation, and you get stronger rotation. So what's causing that? Well, two things. One, increased fire activity, and that's where we get like a feedback circle. We get stronger updrafts. But then the other thing can be the triggering of the Pyro-CB. When we trigger the Pyro-CB, we get a sudden vertical growth of the plume, might double in height in 10-15 minutes. And as it's doing that, it's pulling on the air beneath it. And so if we have these sort of flow dynamics at the surface that have some rotation in them, you can go from weak broad rotation to strong concentrated rotation in a very short period of time. And that seems to be a common signature in the fires that we've looked at that produce these tornado strength vortices, real fire tornadoes. That said, I don't think it's the only way that fire tornadoes form. There are a lot of other complexities, the interaction of different plume elements that can start to rotate, intertwined, interactions with topography that create eddies that get stretched out, and then interactions with other airflow boundaries, like a front moving across or an outflow, drainage out of a canyon. There's all sorts of things that can lead to it, but I do think this flow splitting, rotation, and then favoring one or the other is a fairly common signature right now for the really impressive events. So a lot to learn though still about what's going on in that environment.
Oh man, that was mind-blowing right there. I'm so glad I asked that question, because that was something I've wondered for a long time, and you just perfectly explained it right there. Love the analogies too. But I've taken enough of your time. You're nice enough to talk to me, answer all my questions, and you literally answered them all perfectly. So thank you very much, Neil.
Yeah, thanks for reaching out, Holt, and hope to talk again sometime soon.
Oh yeah, definitely.